Question 9 is about a geosynchronous satellite, and the first part, state two features of a geosynchronous orbit. Well, there's no point me telling you here because you'll only forget it again, so look it up in your book. One of the features is to do with the time period, the other feature is to do with whereabouts the orbit's got to be, what plane the orbit's got to be in. Part B gives you information about the mass of the Earth and the radius of the Earth, and it says show that the radius of a geosynchronous orbit must be 4.23 times 10 to the 7 metres. Now remember, when a question says show that a value must be something, all it means is work it out, and when you get the answer, it'll be the thing that's given there. Now it's important to be able to work this question out for what we might call first principles. So not by having learnt all the details of this particular question, but by basic stuff that you can rely on knowing about satellites and about orbits. And if you're a bit rusty, we'll look at the data sheet. And we've got to ask ourselves, why is this satellite in orbit? Well, the reason the satellite doesn't go off into space is because it's being held in its orbit by the gravitational force between two masses, M1 and M2, where in this case, M1 could be the Earth and M2 would be the mass of the satellite. And we also say what sort of orbit is it in? Well, it's in a circular orbit. When something's in a circular orbit, it means we're dealing with centripetal force. And if we've forgotten it, we have a look at the data sheet for centripetal force, and we see that we've got centripetal force is mv squared over r, or there's also another way of writing it with angular velocity in. So I would start this question by writing F equals, it's the gravitational force. So it's G. I'm going to write a capital M for the mass of the Earth. I'm going to write a little m for the mass of the satellite over r squared. So that's a gravitational force that's doing it all. What's it doing? It's making the satellite move in a circle. And remember that the force that makes something move in a circle is what we call the centripetal force. So we've got the formula from the sheet for centripetal force, mv squared over r. So capital M, mass of the Earth, little m is mass of the satellite, and in the centripetal force, little m is the mass of the thing that's going round, so that's the satellite. So when we've got that equation down, we can start simplifying it. So gmm over r squared equals mv squared over r, so we can see that we can rewrite that with a few less things in. Still need the g, still need the mass of the Earth. We don't need the mass of the satellite because it's going to cancel from both. And instead of dividing here by r squared, we just divide here by r. And on the other side, we don't need the m, we just need the v squared. We don't divide by r because we've cancelled out that dividing. So gm over r equals v squared. Then we've got to ask ourselves, what do we mean by the speed? Well, speed means distance over time. So for something going round in an orbit, the speed, it's the distance it goes round, 2 pi r, the circumference of the orbit, divided by the time, and capital T is the time period, how long it takes. So if that's what v is equal to, we can write gm over r must be equal to that squared. So 2 pi r over t squared is 4 pi squared r squared over t squared. And the question is about the radius of the orbit. So let's sort out this equation so it tells us the radius of the orbit. So we're dividing by r here, we've got r squared there, so let's put all the r's together. If that r goes there, we've got r cubed, so we get r cubed on its own. The way to rearrange everything here to get r cubed is r cubed equals g m t squared divided by 4 pi squared. Now you're not expected to remember this equation. What you're expected to do is you're expected to know the basic ideas. So the basic ideas was up here. An even more basic idea is the idea of what speed means, and from those basic building blocks you sort out for yourself this equation. So there's an equation for r cubed. We're trying to find r, so we just take the cube root of all that lot, you put all the numbers in, you get the answer, and the answer will be 4.23 times 10 to the 7 metres. Next part of this question Calculate the increase in potential energy of a satellite of 750 kilograms when it's raised from the Earth's surface into a geosynchronous orbit. So the increase in potential energy. Now we avoid any temptation to try using MGH. If we're lifting this satellite up a few metres, yes, we'd use MGH, but when we're going right out into this geosynchronous orbit, obviously we don't use MGH, so we have a look at the data sheet. What is there on the data sheet to help us deal with energy in fields? And hopefully we recognise that gravitational potential is to do with the potential energy. We remember that gravitational potential is the potential energy per kilogram. And we've got a formula for it here. V equals minus G big M over R, where big M in our case will be the mass of the Earth. Just remember that the minus sign is quite significant with gravitational potentials. Now we're looking for the difference. We want to know how much you've got to increase the potential energy when you take it from the Earth's surface into the geosynchronous orbit. So what you need to do is you need to work out what's the potential on the Earth's surface. So we use this formula, Gm over R, and the first time we use it, we use in the radius of the Earth. That gives us the potential at the Earth's surface, which you might remember having done before and getting minus 63 megajoules per kilogram. Not expected to remember that, but you've got the numbers to put in. That's the answer it will give. The next thing you've got to do is you've got to work out the potential at the radius that's the geostationary orbit. So you've got this value here, 4.23 times 10 to the 7 metres. So what you've got to do is you've got to use this formula again for potential. This time you're finding the potential at the radius of the geostationary orbit. So much bigger value of R, so the potential will be a smaller number. It's still a negative number though. So the potential goes up. When you go from the Earth, you're going from minus 63 megajoules per kilogram to something that's still negative, but not as negative. What you've got to do, when you get those two values for potential, you can find the difference between them. And the difference in potential tells you how much energy you've got to give each kilogram of the satellite to lift it from the Earth's surface up to this new orbit. Because potential is potential energy per kilogram. Then you've got to remember that you're dealing with 750 kilograms. So you work out the total energy for the whole thing. So for part C, it says that satellites in orbit nearer to the Earth than geosynchronous satellites may be used in the future to track road vehicles. State and explain one reason why geosynchronous satellites would not be suitable for such a purpose. Well, the important thing about this is if you're trying to track an individual road vehicle, you've got to remember that a geosynchronous satellite, 4.23 times 10 to the 7 metres, 42,000 kilometres away, would you be able to get a signal from 42,000 kilometres away that could pick out individual cars? And the answer is that you couldn't. You couldn't get an image that was clear enough of an individual car. So that's why geosynchronous satellites aren't suitable. Not some of the things that some people, but the fact that the cars are moving and the satellites aren't. That was an irrelevant thing. The important thing is that these satellites are so far away from the Earth that the signal from an individual car would be too weak, or the satellite wouldn't be able to distinguish between individual cars. The last part, give 2 points you would make in favour of tracking vehicles or 2 points against. And although a lot of people had good points, the mark scheme was quite clear that you had to use 2 points that were both in favour or 2 points that were both against. The question's not so clear on that, is it? But the mark scheme was. Question 10, a small charged sphere suspended from a thread. And there's a picture of it, and we see that instead of hanging straight down, the sphere is dangling at 6 degrees away from the vertical. So why would that be happening? Well, it must be because there's a sideways force. Where's the sideways force coming from? It must be caused by the electric field, because the sphere has got a charge on it. And the first thing you've got to do, show that the electrostatic force F on the sphere is given by F equals mg tan 6 degrees. So how do we do that? This isn't really a fields question, this is a forces question. This is going back to Unit 2 from AS. So let's draw a picture. There's the string, there's the sphere, there are some forces on it. The forces on the sphere, it's got some weight, mg acting downwards. It's got tension in the string, and the thing that the question's about, this electrostatic force. And since the thing's dangling to the right, the force must obviously be to the right. So that's F. So those are the forces. F's supposed to be horizontal. Doesn't look very horizontal, does it? So, how do we show that that equation is right? F equals mg tan 6 degrees. Well, the easiest way to do it is to think about this tension. What's the tension doing? Part of the tension is supporting the weight. The other part of the tension is balancing out the force to the right. So we've got T has got two components. One of them will be T sine 6 degrees. The other one will be T cos 6 degrees. Because that's always what the components are. There's always one that's sine and one that's cos. All we've got to do is get these the right way around. One of these is mg and one of them is F. And the way that I'd do it, I'd think about, what if the angle wasn't 6 degrees? What if the angle was 0 degrees? The string would be dangling straight down and T would equal mg. So if the angle was 0 degrees, which of these two, would it be T sine or T cos that would give a value just of T? And of course it would be T cos. T cos 0 degrees would just be T. So it must be that T cos 6 degrees, that must be the thing that balances mg, and therefore T sine 6 degrees, the other component, that must balance F. So we've got two equations, we've got F and mg that we want, we've got the 6 degrees that we want, but both equations have got T and we don't want that. How do we get rid of them? Well, if we remember that sine 6 divided by cos 6 is tan, and if you don't remember, you know that sine is opposite over hypotenuse and cosine is adjacent over hypotenuse. If you divide sine by cosine, you get opposite over adjacent, which is tan. So if we divide these two equations, T sine 6 degrees divided by T cos 6 degrees, well, since F is the same as T sine 6, I can put F, and since mg is the same as T cos 6, I can put mg there. So it does work to divide equations. The T's cancel, I get tan 6 degrees is F over mg, so F equals mg tan 6 degrees. Part B, calculate the charge on the sphere. The question tells us what M is, so we're able to work out F. We also know what causes F. F is caused by being in an electric field. And if we're a bit rusty, we'll look at our data sheet. When you've got a charge in a field, F equals E times Q, where E is the field strength. So we can write F equals EQ. So that's an equation that links F and Q, which would be okay, provided we knew what E was. It's two parallel plates. So we have a look at the data sheet. The field strength for a uniform field, E equals V over D, which must mean that F equals V over D times Q. So we use this equation to find the value of F. We then know what V is, we know what D is, we know what F is, so we find Q.